Mr. Ted would be great. And I'll be back in a minute.
All right, thank you, Lee. So thank you for letting me talk here today. I'm going to briefly describe 4 different things. One, I'm going to give a brief survey of the results that have been obtained over the last 2 to 3 years of simulation for binary black holes, numerical simulation. Then I'll go into a little more details about one particular project that we've done here in the Caltech Cornell collaboration, where we compare a numerical relativity simulation to the waveforms from a numerical simulation to those predicted by post-Newtonian theory. Then I'll spend a few minutes describing a fun little project where in which you try to guess the final spin of the merged black hole just from basic test particle principles rather than doing numerical simulations. So it gives results that agree surprisingly well with the numerical simulations in the cases simulated so far, though those cases are all, as I'm describing, are not completely generic yet. And then, since I recently was at a workshop at Santa Barbara at the Caltech Institute of Theoretical Physics on the interface between numerical relativity and data analysis, I was asked to say a few words about what happened during that workshop. So basically, there has been a revolution in the simulation of binary black holes in the past 3 years. Prior to April of 2005, no one could simulate the end-spiral merger and final ring down of 2 black holes coalescing due to the gravitational waves that they emit. Franz Pretorius, who was a postdoc at Caltech at that time, did the first successful simulation using a method that basically was not being used by anyone else in the community. In it, this method now has become known as generalized harmonic formulation of moving decision. What the generalized harmonic refers to is just a formulation of how Einstein's equations are solved. And basically, in this type of system, they're treated as 10 second-order wave equations, one for each component of the space-time metric, and they're coupled and highly nonlinear. And a key feature of what Franz did was that previous simulations had been plagued by what are called constraint violations, like Einstein's equations, like Maxwell's equations. You solve them by taking some initial state and trying to evolve that state into the future through a set of different partial differential equations. Like Maxwell's equations, there are certain constraints, say div E and div E constraints. There are similar constraints in Einstein's theory, which must be determined on the initial slice and which must be maintained as you do your evolution into the future. And prior to 3 years ago, numerical simulations would not satisfy this without numerical simulations had a hard time preserving these constraints as you evolve in time due to numerical errors, where you know from the theory that they should be preserved. And Franz was able to modify the equations to introduce terms which damp these constraint violations, and that led to its success. He also used full adaptive mesh refinement, which was a key in order to get enough resolution to do the problem. Motivated by his success, people tried to work harder, and in late 2005, the moving puncture method was developed independently by 2 groups, one at Texas Brownsville and one at NASA Goddard. And this way of solving the binary black hole problem was more in line with what people had been attempting to do in the community. It used a formulation of the equations which was used by most groups. The key idea here is that instead of excising the singularity of each black hole from the grid, you replace them with what's called a puncture. And this puncture basically represents the strong field near the black hole, and you let them move through your grid. Now, no one thought this would work before it was done because you have these massive singularities going through the grid. But if you use sophisticated coordinate conditions called these gauge driver conditions, then you're able to control these punctures so that the singularities are actually pseudo-excised from your grid and then propagate through and not cause polymers. The key to this method is that it was quickly adopted by multiple groups. Now there's at least 10 groups in the world that use this type of method to do binary black hole simulations. So now I'll just go into a sampling of the results. The first binary black hole simulations concentrated on equal mass binaries where neither black hole was spinning. And here's an example of the waveform that's produced in this case. You have the in-spiral phase here where you only have 1 or 2 orbits before the black holes are merged in this particular simulation. Then the merger occurs here, and then the final black hole rings down. For this case, this merger phase was very simple. The transition between the in-spiral and the ring down only consists of 1 or 2 gravitational wave cycles, and it just smoothly connects the two regimes. This regime was known by the post-Newtonian theory to be just a chirping signal, and the ring down can be studied by through perturbations of black holes. What was not known before the simulations was how these two joined, and it seems that the physics here is very simple. For the equal mass non-spinning case, about 3.5% of the energy is radiated during the last orbit ring down merger, and if you add on the entire post-Newtonian in-spiral phase, you might get up to 5% of the energy. And more importantly, for astrophysical purposes, if you have 2 non-spinning black holes merge, the final spin of this object has a curve parameter of about 0.7. The gravitational waves are dominated by quadrupole radiation emission, the 2-2 mode. When you decompose the waveform into spin-weighted spherical harmonics, accounts for 98% of the energy loss. From the initial simulations 2 years ago, which basically covered 1 orbit plus merger and ring down, the community has been able to push this case to doing multiple orbits. In the case of our group, we can now do 16 orbits plus the merger and ring down. And this allows you to do precision comparisons with post-Newtonian calculations. And I'll describe this in more detail later in the talk, because you expect the earlier you go back in the in-spiral, the better post-Newtonian theory will describe the early in-spiral. Also, to date, the only comparison among different codes has been done on this particular case. This compared the initial waveforms produced by Franz, the Brownsville, and Goddard groups, and you see that qualitatively they're quite similar. The runs by Pretorius and the other 2 are slightly different because they use different initial conditions. The runs by Pretorius were more eccentric than those done by the Goddard and the Brownsville groups. Now when you move to unequal masses, but still keeping the black holes not spinning, there are a few new features introduced. The energy radiated decreases basically as the mass ratio squared. The final spin also decreases as you increase, as the masses the ratio between the masses increases. Since gravitational radiation is emitted asymmetrically in this case, you get linear momentum is radiated in a particular direction. This direction in which it is predominantly radiated changes in phase with the orbital phase, but at some point the merger occurs, and that means that there'll be more linear momentum ejected in a particular direction, this has a back reaction on the final black hole gaining its kick. And this was studied by several groups, and Gonzalez et al. Did a comparison, which I've plotted here on the right, which shows the kick velocity along this axis. This value is about 150 kilometers per second, for several values of the symmetric mass ratio, where 1/4 is equal masses and you get no kick, out to the peak of this curve happens at a mass ratio of about 2.77, where you get a kick of 175 kilometers per second. This is enough to eject black holes from maybe very small galactic clusters, but not enough for more massive galaxies. Another thing that's been done more recently in the unequal mass non-spinning case is work has begun on construction of templates which can be used in LIGO data analysis. This group has fit 7 numerical simulations, attached them to post-Newtonian waveforms earlier in the spiral, and then use these to construct a analytic template bank which can cover the in-spiral merger and ring-down phases as a function of mass ratio for non-spinning bodies. And they've tested this then on 30 other waveforms that they've also produced to test this analytic template. And you can do comparisons between looking for the signals with your theoretical template. And they found in the cases they've found that the fitting factor between the analytic template and the signals they look for are all have fitting factors of 99% or in that range. So they believe that at least for non-spinning binary black holes, that only a few number of simulations will need to be done in order to construct a template that will be adequate for detection purposes in LIGO. Now when you let the black hole start spinning, you get more interesting features in the dynamics. On the left-hand side, you have equal masses and the spins are equal and aligned with orbital angular momentum. And on the right-hand side, again, equal masses, equal spins, but the spins are aligned opposite the orbital angular momentum. And what happens in this case is that there's a definite change in the orbital dynamics. The aligned case has to go through more orbits in order to radiate enough orbital angular momentum away, so the final angular momentum of the merged hole is guaranteed to be less than 1. Also, just the potential based due to the spin orbit interaction is also responsible for the difference between these two curves. The final spin of the black hole in both cases is still aligned with the initial orbital angular momentum. In this case, it can range from estimates are up to 0.95 for maximal spins. Aligned, and I'll say again a bit more about this later, to about 0.35 for the anti-aligned case. Another interesting feature is that now for the equal mass case, you can have kicks if the spins are not equal. And so again, linear momentum will be radiated in a preferential direction. The kicks from unequal spins can be as high as 475 kilometers per second if you scale to maximum spinning black holes. So this is about 2 to 3 times the value found in the unequal mass case. So this type of kick starts to be interesting.
What is the green?
This green is the shape of the apparent horizon, or shape of the horizon at the merger. So, I mean, these are crude simulations compared to what we can do now, so I'm not sure how much you should believe that shape. And it's also dependent on the coordinate conditions you choose during your evolution as well. Once the spins are no longer aligned with the orbital angular momentum, then you can get precession effects of the orbits and spins. Here's a simulation where if the orbital plane is the XY plane with the orbital angular momentum going in this direction, the spins are initially in this direction. And as the system evolves, the orbital angular momentum will tilt because the orbital angular momentum and the spin momentum want to precess about the total, the sum, the J vector, summing the L and the S. So they both precess about it, so you get the orbital plane changes significantly, practically tipped on its side by the time you go through a couple orbits with your merger. Another unexpected feature was that the kicks due to the spins can now be as high as 4,000 kilometers per second if you scale what's been done to maximally spin black holes. And this maximum kick comes from the configuration where you have your orbital angular momentum vector pointing up, and you have one spin pointing in this direction, one spin pointing in this direction, maximal. And the linear momentum in this case is ejected sinusoidally in the z-axis. And so what happens is the orbital plane bobs up and down depending upon the orientation of the initial, well, depending on the orientation and where you are in the sinusoidal bobbing, which happens when the merger actually occurs. You can either get no kick if you go to the wrong spot, or you can have a kick that can be as high as 2,500 kilometers per second in the simulations that have actually been done. But if you scale that to maximum spinning black holes, it can be as large as 4,000 kilometers per second if you take the scaling that looks like it's happening for spins up to 1.8, 1.9. So in the past year, there's been an industry trying to develop fitting formula for these kicks based on post-Newtonian formulas that I did as part of my thesis work 13, 14 years ago. So you take the form of this post-Newtonian equation and then you fit coefficients to it based on numerical simulations. And they can get these kicks to within several percent in the cases that have been looked at so far. But of course, the more simulations you do, the better you can improve these fitting formula. These fitting formula will be interesting for astrophysicists who want to know how these kicks occur in binary systems. But it also has to be coupled in with studies which look at the distribution of these of the spins, because this particular orientation that gives the super kick results may not happen very often in nature, so you have to fold that information.
Are there hang-ups?
So certainly in the case where both spins are aligned with your orbital angular momentum, the evolution proceeds. You get more orbits. So far, it doesn't look like it hangs up. This type of behavior follows what you would expect from even post-Newtonian analysis. You just have the potential, the rate of in-spiral is changed by the spin-orbit coupling, and so you know that this case is going to in-spiral slower than this particular case. But it still looks like that it's a fairly smooth in-spiral. It doesn't stop at some particular point. You can't go on. Now, the highest spins that have been simulated to date are about 0.9, in the 0.8 to 0.9 range. So if interesting things happen as you push the curve parameter towards maximal, then we don't know the answer yet. I'll talk a little bit more about predictions of the final spin, and if you believe these these estimates, so far, it looks like you can't get orbital hang-up, that you'll always have final spins that will smoothly spiral together. There haven't been very many simulations so far of generic binaries, that is, that have unequal masses and precessing spins. There's only been, I would say, less than 5 simulations that have been published that I know of that do a generic binary. And the reason is these simulations get more expensive as mass ratio and spins increase. However, given that this is probably going to be very interesting to LIGO, this is expected to be a big focus of simulations in the future this year. The other interesting thing that had the Rochester group have been looking at is looking at 3-body interactions. And I just want to mention that in case something else. So now I'm going to switch over and describe in a little more detail the results of a recent paper we've written here at Cornell and the Cornell Caltech collaboration on comparing post-Newtonian waveforms with those of numerical simulation. These will concentrate on an equal mass non-spinning binary because that's the one we know best. The idea here is to compare the numerical simulations with the post-Newtonian simulations. We want to test post-Newtonian in the latent spiral and see where it breaks down, where we want to test our code in a regime where we think post-Newtonian is valid. So we want a long, accurate numerical simulation in order to do this. So we use here at Cornell what's called the spectral Einstein code, which was developed by myself, Harold, and Pfeiffer, and Mark Shield, and used by the Cornell Caltech collaboration. This uses the generalized harmonic formulation of Einstein's equations, just like Franz Pretorius used in his breakthrough simulation. However, our code needs it to be written as 10 coupled first-order wave equations instead of as 10 second-order wave equations, so we have to introduce extra variables. Instead of involving 10 variables, we're involving 50 variables, 10 for the components of the space-time metric and 4 derivatives for each one, time and spatial derivatives. And we in addition, have to use constraint tables like Franz. Pretorius let his black holes move through the grid and had the excision regions cutting away the singularities moving through the grid. During his evolution, this does not work in our spectral code, so we had to come up with what's called a dual frame method, in which we have 2 frames, one computational frame in which the excision, the excised spheres around each black hole are fixed, and then there's a coordinate mapping that relates this frame to the frame which is the inertial frame through which the black holes move. In order to get this to work, we have to use some ideas from control theory to adjust this mapping between the 2 frames to track the black holes doing some type of time-dependent rotation and scaling. Also important are the boundary conditions we use. The excision regions around each black hole are pure outflows, so we don't need the boundary conditions. Our outer boundaries try not to introduce any constraint violations, incoming physical radiation, and minimize reflections due to coordinate conditions. And we use what is called the multi-domain pseudospectrum method, which has exponential convergence for smooth solutions, and therefore is highly efficient with high accuracy. So we do a simulation, we watch the black holes go through 16 orbits, and we compute what is called psi4, which is a component of the Weyl tensor, which is related to the gravitational radiation. And in order to do this, we have to extract these gravitational waves as a series of radii surrounding the black hole, which are coordinate spheres centered on the center of mass of the system. In this talk, we'll just concentrate on the 2-2 mode and decompose this psi4 into modes with respect to spin-weighted spherical harmonics, and we'll only look at the dominant 2-2 mode, which, as I said, carries about 98% of the energy in the constant case. And given this 2-2 mode of psi 4, this is a complex quantity, and we'll find amplitude and phase as you would for any complex variable, except for this minus sign, because we want the phase to increase as the simulation goes. And the gravitational wave frequency will just be given by the time. We'll define that as the time derivative of the phase. So we extract these gravitational waves at a set of extraction spheres ranging from 75 times the total mass of the system to one at 240 times the total mass of the system. And we're going to fit the phase and amplitude of psi 4 as a function of the retarded time and the extraction radius. And that will be some power series in 1 over r. And what we want is we want the piece that's left at infinity, so we have a bunch of coefficients, we fit them, and we just keep these, we identify the phase and amplitude at infinity just by looking at the terms. Now we want to compare these numerical waves, which we've extracted and extrapolated what their value should be at infinity, to those from a post-Newtonian approximation. Now, a post-Newtonian approximation is a slow motion, weak field approximation to general relativity, and an expansion parameter, which is related to the mass over the separation of the two bodies, or the velocity squared. You can solve the relativity and write down a set of equations of motion which give you the acceleration, the binding energy. These have been computed through what is known as 3.5 post-Newtonian order. The radiation reaction, that is the emission of gravitational radiation, will change the acceleration starting at 2.5 post-Newtonian order. So if you had just computed the equations of motion through second post-Newtonian order, you would get no in-spiral at all. So when you're talking about post-Newtonian approximations, you have to be careful about whether you mean the post-Newtonian order with respect to the radiation or the motion. Similarly, you can predict the gravitational waves emitted in this theory. The energy flux has been computed through 3.5 post-Newtonian order, and the polarization waveforms H plus and H cross have been computed 2.5 post-Newtonian order. In order to produce accurate templates, what you do is you assume that there's an adiabatic in-spiral of quasi-circular orbits. This gives you a frequency, and you use energy balance, which I'll describe in a minute, to give you a sense of how this orbital frequency evolves in time. So we know that quasi-circular orbits will be a good approximation because the emission of gravitational radiation circularizes the orbit, so that as binaries get to the LIGO's bandwidth, the eccentricities will be quite small. This allows us to express in the energy flux and the waveforms in terms of an orbital frequency parameter and the orbital phase. That's just a circular orbit slowly in-spiral. For instance, for equal mass non-spinning binary, the energy is given by this expression, and the flux is given by this expression in terms of this orbital frequency. And here you see the flux is known to 3.5 post-Newtonian order energy. Similar. Now, as I mentioned, the polarization waveforms are known to 2.5 post-Newtonian order. You can write down the polarization waveforms and you can decompose those in terms of spin-weighted spherical harmonics as well. The polarization waveforms to 2.5 post-Newtonian order, what you have to do is you have to evaluate these radiative multiple moments to sufficiently high order. And then the post-Newtonian counting works by counting powers of C, so each higher power of C is one more order in the post-Newtonian expansion. So given that the multiple order increases with this L, you see that you only need a finite number of these multiples to compute the polarization waveform to a given post-Newtonian order. And since higher modes enter at higher orders, each one series here is only known to 2.5 post-Newtonian order. However, you can compute these modes directly from the multiple moments themselves. That is, the 2-2 mode will only depend upon the radiative mass and current multiples, quadrupoles essentially. And it turns out that the limits, the knowledge of the multiples that limit you to 2.5 post-Newtonian order do not come from the dominant quadrupole mode, that is the L equals 2 mode, but from a higher order mode. And therefore, if you were to just use your knowledge of these radiative multiple modes to compute just the 2-2 mode, you can actually compute it to 3pn order. It's actually knowledge of these modes which are limiting you into the order in which you can compute the full polarization waveform. So therefore, when we do numerical simulations, we don't have a detector looking at a source in a particular direction. We actually know the waveform everywhere. So we can exploit this knowledge and compare the amplitude to a higher order than we would be able to, for instance, in LiDAR. So in particular, I computed the 2-2 mode for an equal mass non-spinning binary. Actually, I've done it for arbitrary masses and non-spinning binary through 3p order. So then you introduce the concept of energy balance. You say that the time rate of change of the orbital energy is going to be exactly balanced by the amount of energy carried away by gravitational radiation. So given an expression for orbital energy in terms of orbital frequency, the energy flux in terms of orbital frequency, and the waveform in terms of orbital frequency, you need to choose 3 things in order to build your post-Newtonian waveform. You need to choose the order through which you keep terms in the expressions for the energy and luminosity. Those are typically kept up to 3. You can go up to 3.5 post-Newtonian order. You can compute the order through which terms in the waveform are kept. And then you have to choose how to use this energy balance equation to derive an expression for the time rate of change of the orbital frequency in terms of these 2 series that you already know. And it turns out that there's at least 4 different ways, simple ways you can think of doing that. One is you have these 2 expressions as ratios of post-Newtonian series. So you could just numerically integrate that ratio to get and solve this coupled set of equations to get orbital phase and orbital frequency as a function of time. You can analytically integrate. You can move this to the other side and analytically integrate this expression to get the time and phase as a function of gravitational wave frequency implicitly. Once you have that, so then you have just, in this case you have a numerical solution, in this case you'll have an analytic solution. You'll have expressions for t of x and phi of x, so this is some series, power series in x. The Taylor T3 wave approximate comes about by inverting this expression for t of x to get some expression for x of t by expanding in a small post-Newtonian-like parameter. And then finally, you could have, instead of numerically integrating this ratio of post-Newtonian expansions, you could have re-expanded this fraction as a Taylor series and then numerically integrated that result. And that's, we call it Taylor T4 to be consistent with the name of the other ones. So what we're going to do is we're going to equate the post-Newtonian total mass to twice the irreducible mass of each black hole, because you were defining what the mass of a black hole in a binary is not well defined in the theory. We're going to compute a post-Newtonian psi 4 by taking 2 time derivatives of the polarization waveform. We're only going to compare the 2-2 modes, and at a given matching frequency, we're going to perform a time shift and a phase shift so that the times at this particular matching frequency and the phases at this particular matching frequency are equal. But before I show you the results of this comparison, here are some estimated error bounds on different things that will affect this comparison. Both in the number of radians, these sources of errors will introduce this much error in the phase given in radians, and this percentage difference, relative error in the amplitudes. So we considered numerical truncation error, that is just, did we have enough resolution in our simulation? We can reduce this to 3,000ths of a radian. Then there's the issue that we have a finite outer boundary in our grid, and depending on where we put this outer boundary, can introduce errors again on the level of several thousands of radians. Then we have the fact that we're extrapolating our waveform based on extraction of a given set of extraction spheres, and we estimate that error. Other issues are we extracting these, are our extraction spheres basically remaining spheres? Do we have any change in the mass of our black holes as they're inspiraling each other? Is the coordinate time we use in our simulations related to time as seen at infinity? And then there's the fact that even though we tried to make our numerical simulation correspond to a quasi-circular n-spiral, we do have some residual eccentricity, and we have some residual spins on the black holes. And these actually dominate the phase errors in that comparison. So two previous groups had attempted to compare post-Newtonian and numerical simulations. The CaJAGWR group did a simulation lasting 7 orbits, extracting at a radius which was fairly close given the ones we choose. And they found that post-Newtonian and their simulation agreed to within about 2 radians over this in-spiral wave. But this is also within about their estimate of their numerical errors. So for most of this, the post-Newtonian and numerical waveforms were consistent within their numerical errors, and only during the very last orbit during in-spiral did you see any difference. The CaJAGWR group did a comparison of 9 orbits with a more accurate code, extracting in a series of extraction spheres, which allowed them to extrapolate the amplitude as a function of phase to infinity, but not each of them separately like we were able to. They estimate their accuracy of their code in phase to be about 0.25 radians and their amplitude accuracy to be 2%. And they did it for 2 different models of 2 different approximates of post-Newtonian theory, and found phase differences for Taylor T3 on the order of 0.2 radians and Taylor T1 on the order of 0.8 radians. If they match late, if they match earlier, you see that at late times, the post-Newtonian approximates diverge by roughly 1/6 of 0.8 radians. Now for our results, I'll show you 2 different cases. Taylor T1, where you numerically integrate this ratio of post-Newtonian expansions. And we find that if we match lates, we get phase differences that approach 1.5 radians at early times. And that even as you go towards matching at earlier times, you really have to start matching at a very early time to get consistency between post-Newtonian and numerical waveform. This is about 10 orbits before merger. Taylor T2 and Taylor T3 are fairly comparable in errors like this. However, when we looked at this Taylor T4 approximate, we found to our surprise that even when matching late, the phase differences between the post-Newtonian and numerical simulations are consistent within our numerical error, our error estimates over the entire in-spiral. differences between the different post-Newtonian approximates. There's no a priori reason why you should prefer one approximate over another. So given the wide spread between them as you increase the order, matching late, we've matched the waveforms at an early frequency, and this as a function of post-Newtonian order for these different approximates is showing the phase differences. So we see fairly early in the end spiral, at least as you increase the order, the spread of the approximates is going down, which gives you, maybe in this regime there is some convergence with post-Newtonian theory, but here the spread is still quite far between the different approximates, and this suggests that Taylor's E4 just got lucky with this particular case. You can also look at varying the post-Newtonian amplitude order. So for our best post-Newtonian phase evolution of T4, here all we've done is kept different amounts of terms in we've varied the order of the number of terms you keep in the post-Newtonian series expressing the amplitude. And so you see if you keep just what are called restricted post-Newtonian waveforms, the error in the amplitude can be on the order of 6–7%. Again, the series is not monotonically increasing and convergent as you increase the post-Newtonian order, but we do see that keeping the full 3pn waveform, at least for the 2-tube mode, can reduce the amplitudes a lot, which suggests that it might be good to keep the full 3pn amplitude. More recently, the Gained group has done another comparison between post-Newtonian and numerical relativity for equal masses, but now with spins aligned with the orbital angular momentum, varying the black hole spin from 0 on the left to 0.8 here on the right. Spin orbit effects in the post-Newtonian theory are not known as well as the non-spinning effects. They're only known through 2.5 post-Newtonian order as opposed to 3.5 order in the non-spinning case. Therefore, you don't expect the post-Newtonian expressions to do as well as you increase the spin. And here we see they again get good agreement for Taylor's E4 when the black holes are not spinning. But as you increase the spin, you see that the Taylor's E4 can rapidly goes to errors of a radian or more, so suggesting that it's good agreement in the equal mass non-spinning case was just a coincidence rather than okay, so done with that comparison. Now I'm just going to describe a simple model for estimating the final spin of the black hole. So astrophysical parameters of the final black hole that are most commonly you want to know are the final mass, final spin, and the recoil velocity. And there's going to be some interplay between numerical simulations, post-Newtonian arguments, and test particle arguments to develop a formula that can predict what these quantities are as a function of the initial spins and masses of the binary. This is work I did with Alessandro Bolano and Luis Lehner. And what we did is we wanted to see if, just given simple arguments, you can guess the final mass, the final spin of the black hole given the initial spins and the mass ratio. So what we do is we have a simple model where we just assume that the mass of the system is conserved, which is good for a rough estimate because the most energy radiated in any simulation seen to date is about 10%, more typically on the order of 2 to 3%. We're going to assume that the magnitude of the individual spins remain constant during the merger, and that the angular momentum radiated away from the system from near the innermost stable circular orbit to the merger is negligible. So then the final spin is simply going to be the sum of this orbital angular momentum at ISCO plus the individual spins of the black holes. In this case, I'm talking about spins which are either aligned or anti-aligned with the black hole. However, the orbital angular momentum at ISCO is a function of the mass and spins of the system, mass and spin of a black hole. And the key idea for this approach is that we choose this ISCO to be the innermost stable circular orbit of the Kerr black hole with the spin parameter of the final black hole. And so this is now an implicit equation to solve for the final spin of the black hole. So if you do this model and you look at the final spin for a line equal spins as a function of symmetric mass ratio, equal masses are here on the right side, the test mass limit is over on the left side. The different curves correspond to different values of the spins ranging from non-spinning holes in black to maximally spinning holes in green. So in the test particle limit, if you have a non-spinning test particle falling into a Schwarzschild black hole, you would expect the final spin to be 0. Similarly, if you have a maximally spinning test particle falling into a maximally rotating Kerr black hole, you would expect the final spin to be 1. What we find then when we apply our formalism is that non-spinning black holes, when they merge, as you go to the equal mass case, will approach a value of about 0.67, 0.68 for the final spin, while maximally spinning holes will have a value of about 0.95 after you do it. At some critical value, if you have two equal spins, you'll have two initial equal spins will produce the same final spin. If you're below that value, and have equal spins, then the final spin will be higher. But if you're above that value, the merger process is going to lower the final spin. So this would suggest that by just looking at in spirals, you can't maximum spin of the black hole. A similar idea was also postulated by Hughes and Blanford, also using test particle arguments, which are slightly different from ours, but they also predict that mergers alone cannot produce maximum spinning black holes. On the right side, what we've shown is our predictions for having a final Schwarzschild black hole. That is, you have two black holes, their spins are anti-aligned with the orbital angular momentum, but equal to each other, equal spins on the two bodies. And so as a function of mass ratio on this side, going from test particle limit to 0.25 against the equal mass case, as a function of how large the spin is, this is the prediction for where the final spin of the black hole would be 0. So this mass ratio is on the order of about 3 to 1. So for any mass ratios which are closer to equal mass than 3 to 1, you cannot produce a final black hole whose spin is 0. And for, say, a reasonable spin parameter that can be simulated, you have about a 4 to 1 mass ratio is what's required to end up with a final black hole of 0 spin. The interesting thing is that below this curve, the final spin of the black hole is going to be opposite the direction of the orbital angular momentum of the binary. So what you'll see is that the dragging of space-time in the region will actually flip. On the contrary, if you go above here, if you have anti-aligned spins, if you have, for instance, some jets, then you can see them flip after the merger of the curve. So now we've confronted our predictions with numerical results that were done at that time. And on this curve is for initially non-spinning black holes as a function of mass ratio. Our predictions compared with some effective one-body predictions, and then over here in the inset were the known numerical simulations. You see that we get the answers to within a couple percent. Also, if you look at the equal mass case with equal aligned spins, our predictions are in black as a function of the spin magnitude, and the numerical simulations are again, we're in the right ballpark. So given that, we decided to see if we could go get any insight into generic spins, that is where the spins are not aligned with or anti-aligned with your momentum. So you have your aligned momentum pointing in some direction, total spin of the sum of the two spins of the bodies pointing in another direction. So making the assumption that the magnitude of this total spin vector and the angle between this angle theta ls between the total spin and the orbital angular momentum remains constant as the orbital angular momentum shrinks. This gave us a set of two equations, one for the component of it gives you two equations which you can solve in order to predict what the final one of the things you get out of it is what the final spin will be. And this is a series of cases done for generic spins, most of them equal masses, or just one body spinning, but you see in all the cases we get certainly within 5%. So after our paper appeared on the archive, this sparked a few groups to look at this in more detail, to do more simulations, and to look at developing a fitting formula to predict the final spin given the initial conditions. And for instance, there's a paper by Rizzola et al., the AEI group, taking the ideas, borrowing the ideas from the paper to write down a formula fitting the coefficients from known simulations, and this is their percentage error in the final spin versus their fitting formula and some numerical simulations. On this side are aligned and anti-aligned, and on this side are the fits for more general cases where you have recession. So far, most of the numerical simulations have been done either, as I said, with equal masses and spins in some arbitrary direction, or just unequal masses but only one body spinning. These cases are known from post-Newtonian theory not to be the most generic. These cases are known from post-Newtonian theory to have rather simple precession. If you have unequal masses and unequal spins with both body spins, you can get much more complicated expression, precession occurring in the system. And these fitting formula may not work in those cases. We'll need to do, someone will need to do numerical simulations to go through this. So as I said, I recently spent 2 weeks at CaJAGWR on a workshop on the interplay between numerical relativity and data analysis. And these were the main things I got out of the workshop. Several other people also went to the workshop. They could comment on what they learned. So data analysis used to compute a quantity called the match, which folds in the detector noise in order to assess how well waveforms work for detection purposes. So they encourage numerical analysis to compute these quantities. However, for parameter estimation, you want the systematic errors, that is either due to your templates or calibration of the instrument, to be less than the statistical errors. And computing matches is not adequate for this purpose, and there's still a lot of work to do on both the numerical relativity and data analysis side to understand the issues that go into this. And there's really a great need for the data analysis community for a large number of short waveforms covering the parameter space of masses and spin orientations to make sure that there are no holes in their current way of searching for gravitational waves around the world. But also, there is still a need for longer accurate waveforms to construct, calibrate, and test the waveform templates for in more generic cases. And as one concrete proposal out of this workshop is what is called the NINJA project, which stands for Numerical Injection Analysis. And the goal is to test the efficiency of various data analysis pipelines on numerical relativity waveforms buried in Gaussian noise. And the idea is to have all numerical relativists and data analysis be invited to participate in this project. And this project has a web page which you can look up and get more details. I just want to bring this to people's attention in case they want to participate. So basically, in summary, numerical relativity, the numerical simulations of binary black holes have been important to understanding these systems. They can be used to develop templates and fitting formula to be used because it's not possible it's just too computationally expensive to generate these waveforms completely numerically. Therefore, you have to develop templates and fitting formula in order to do reasonable searches. However, there's still a lot of parameter space that needs to be explored, and numerical relativity will always be helpful in testing these analytic models because there's no a priori reason why a given analytic model should be preferred over the other. You need to test it against what you think are real waveforms. All right, thanks.
How far are we from being able to really explore the spin parameter space?
So I think a lot of groups are going to be pushing that. Reasonable spins, I don't think we're going to be doing too many simulations, not a lot of them. I mean, it depends on, there's a balance between how many simulations you can do and how accurately you want to do them. The higher the spins and the bigger the mass ratio, the more resources you need to devote to give a given accuracy. So I think there'll be a lot of very short waveforms which aren't necessarily that accurate, but may be accurate enough for LIGO detection purposes. I think that will certainly happen this year for spins of 0.8 or less and mass ratios maybe 6 to 1, 4 to 1 or less. Then there'll probably be a coarser sampling, just a few waveforms at higher spins and at higher mass ratios in the near future. As computers get faster and we improve our algorithms, this may improve. I don't foresee anyone being able to do maximum spinning black holes for a couple of years. But that's my opinion. Or mass ratio is higher. Just by the techniques that are.
So you said that as you added spin and mass ratios, the orbits changed smoothly. That is to say, there weren't any hang-ups, there weren't any dramatic changes in behavior.
Right.
So is it possible to interpolate and get smooth parameterization of these things without having to go through every single?
No, that's certainly the hope for reasonable mass ratios and reasonable values of the
So you get to these extreme
but
which nature may or may not supply.
But again, there's been not much exploration yet in recessive cases. So how well we'll be able to do interpolation there is another issue.
A question on the kicks. You mentioned sort of the maximum size kicks you expect. What's the size you expect an average in a typical system that's not sort of?
So in reasonable expectations, I think most kicks are maybe in the 400 to 500. There was a study done by Monaro and Schnittman recently, which tried to map out parameter space given an effective one-body model of kicks. And these very high very high kicks only happen in a small number of cases. Their model, their exploration, of course, assumed random distribution rather than trying to fold into any astrophysics about whether or not spins are aligned. If you align the spins, if there are mechanisms that align the spin, either make them aligned or anti-aligned with the orbital momentum, then the maximum kicks are on the order of 500 kilometers per second or less.
And that's something that is basically happening on every inspired orbit that is over.
So to get that maximal kick in the spin case, you have to have one maximal hold this way and one maximal hold this way, and it scales roughly linearly with the magnitude of the spin difference.
So then is it possible to invert the problem, to take the astrophysically observed kick distribution, such it is, and try to work back and find out what the distribution of spins or other parameters might be?
Admirable goal, yes.
One parameter to many, I know, but
Right.
Is there an
such as it is what I mean to say. I mean, sure, people observe high kick objects. There's
So the quasi-circular approximation, is that up to a certain mass ratio? I mean, is there a mass ratio at which that's no longer true? Or?
So the quasi-circular approximation just says I'm in the post-Newtonian approximation, it's just like balancing energy loss carried by the waves with the energy loss of the orbits. And so that is known through 3.5 post-Newtonian order for non-static bodies at any mass ratio. Now, then it spins, you only know the spins at 2.5 post-Newtonian order. Now, at some points, as you go towards the test particle, you do know that the main spiral will end at some radius. But for the mass ratios of simulations done so far, that there's no dramatic change between the main spiral and the Planck ratio. It just looks like a main spiral.
So this has been going on for a couple of years. The true conventional guess is that you detect really high SNR waveforms that will find particles.
Okay, it's
So
not
that
easy.
time comes that.
Right, so, I mean, something that does need to be done on the numerical side in order to test general relativity is to simulate some signals from theories which are not general relativity. And no one's, I mean, maybe a few people have started thinking about it, but no one's done any simulations like that yet.
But how about analytical?
So there have been some post-Newtonian studies that have been done as far as the numerical simulation, because you might hope that it's going to be during that merger phase where you get the strongest deviations between general relativity and the fields are the strongest.
If you have a high SNR waveform, you can always look at the bring down phase and compare it to the in-spiral phase. And that's the test you can do, just sharp compared with beta